Alright, we're going to take just a minute and look over our electrostatics test. I'm just going to work through each problem, kind of talk about what we're going to do. Before we start, I want to take our formula sheet and just annotate it a little bit. Let's start with these equations right here. Those equations right there, we are not going to plug in any positive or negative signs. So this is going to plug them in as all positive right there. And these three equations at the bottom, we'll plug in positive and negative signs as needed. Alright, so let's go ahead and start with number 1. After being rubbed in someone's hair, a balloon has a charge of negative 6.4 times 10 to the negative 9th coulombs. How many excess electrons are on the balloon? Alright, so we're going to use this very first formula right here, Q equals NE. Because we've been given the charge of the balloon, Q. We're asked for how many, which is N, and we're looking for the number of electrons, which is represented by this right here, the charge E. So whenever we see an electron or a proton, we actually know exactly what its charge is. It's listed over here. E equals that number right there. Okay, so let's go ahead and plug in what we got. Again, we're not going to worry about positive and negative signs. We're just going to plug in the numbers. So Q is 6.4 times 10 to the negative 9th. N is the number that we're going to solve for. So we're going to plug in the charge of an electron, which is negative 1.6 times 10 to the negative 19th. But we're just going to plug in the positive version of that. Alright, so let's plug in real quick. 6.4 E negative 9 divided by 1.6 E negative 19. I get 4 times 10 to the 10th. Okay. In our formula sheet, in our answer sheet over here, let's go ahead and fill that in as well. So, how many? It's a positive number. The number is 4 times 10 to the 10th. And the unit, it's really not a unit, just asks for how many electrons. So we can either leave it blank, or we can say, or we can just put electrons for the number of, that's what we're counting. 4 times 10 to the 10th, it's 40 billion electrons, I believe. Alright, let's look at question number 2. So a proton lost 3.2 times 10 to the negative 16th joules of energy and moving from A to B. So what's the potential difference between point A and point B? So let's see what this is. This is the amount of energy. So this is going to be delta PE. This is the amount of potential energy that changed. And we're looking for potential difference, which is delta V, between point A and B. And it looks like we've only been given one thing, which is not enough to solve in any of our equations, but we've been told that it's a proton, and we know the charge of a proton. So right here we know that its charge, Q, is this number right here, the 1.6 times 10 to the negative 19th. So 1.6 times 10 to the negative 19th coulombs. So now we have two numbers, and the equation that relates Q, delta PE, and delta V is that one right there. Nope. That one right there. Nope. That one right there. The one in the middle. There we go. So delta V equals negative, no, I'm writing down the wrong formula. Delta V equals delta PE over Q. And we are actually solving for delta V, so all we have to do is plug in the change in potential energy. Now remember that for this formula we do want to plug in our positive and negative signs. So what is going to be the sign of each of these numbers that we plugged in? So this bottom one is the charge of a proton, so this is just positive. And the 3.2 is listed as a positive number, but the problem actually says that a proton lost that amount of energy. So is the change in energy going to be positive as though it gained, or negative as though it lost? It's going to be negative because it lost that amount. So we'll do that right there, and let's see what we get. negative 3.2 E negative 16 divided by 1.6 E negative 19. We get negative 2,000. And since we're solving for potential difference, the unit there is the volt. There we go. Go over here and fill that into our answer sheet real quick. So it's going to be negative 2,000 volts. There we go. Keep going. At a distance of 0.05 meters, a charge Q is creating an electric field with a magnitude of this. So this is our electric field E. That points in towards itself. What's the charge Q of the particle? This distance right here could either be D. Some of our formulas have D for distance. Some of them have R to measure distance. But this question is actually asking about the electric field created around a charged particle. So that is actually referring to this formula right here. This is the electric field created by a charged particle Q at a distance R. So this actually represents R right there. Even if you didn't know which one to use, R or D, there's only one formula that relates E, Q, and a distance. The other one that has E, Q, and distance in it also requires the change in potential energy, which we haven't been told anything about potential energy, so it can't be that one. Alright, so E equals KQ over R squared. So we'll plug in 3.6 times 10 to the 6th equals K. Now the value of K is listed up here. K is 9 times 10 to the 9th. Q is actually what we're solving for. And R is 0.05 squared. Okay, so in order to solve for Q, we need to multiply by 0.05 squared and then divide by 9 times 10 to the 9th. So let's do that. 3.6 E6 will multiply by 0.05 squared. 3.6 multiply by 0.05 squared, and then we'll need to divide by 9E9. And we get 0.00001. Now, I'm going to actually switch this to scientific notation so it'll be a little easier to read. So I'm going to hit second science and flip it from float over to scientific notation. Get 1 times 10 to the negative 6th. That gives us Q equals 1 times 10 to the negative 6th, and the unit for charge is the coulomb. Now, this formula, we plugged in all positive numbers, which means that this Q isn't necessarily positive. It could be positive or negative. So let's go back and remember what the electric field means and what an electric field that points in toward the particle means. So let's draw out our two options. One is a positive particle, one is a negative particle. If you remember, the electric field tells us the direction that a positive charge would go. So if we put a tiny positive particle right here, where would it go? It would be forced away from the positive particle. If we put a positive particle right there, which would it be forced away from our positive particle. So no matter where we put it, it will be forced away from our positive particle. Let's look at our negative particle. If we put a positive particle right there, which way would it go? Well, it would get forced in toward the negative particle. If you put a positive particle right there, it would get forced in toward the negative particle. So no matter where you put this little positive charge, it's always going to get pushed in, down toward the negative charge. So this one is saying that the charge is creating an electric field that points in towards itself. So is that telling us it's positive or negative? Well, it's got to be negative. So this is a negative Q. Let's go ahead and fill that into our formula sheet, our answer sheet over here. So it'll be negative 1 times 10 to the negative 6th coulombs. All right, number 4. A particle gains 9 joules of electric potential energy. So this 9 joules right here is delta PE, or change in electric potential energy right there. As it moves 0.4 meters, so that's the distance that it moves. Notice that all of our formulas that have to do with distance are down here with the change in potential energy. So if you have change in potential energy in a distance, we're gonna use D for distance and not R for distance. All right, and they give us the electric field E, and they're asking for the charge of the particle. So what formula relates delta PE, Q, E, and D? That would be this one right here. Delta PE equals negative QED. Okay, so it gains 9 joules, so we're going to plug that in as positive 9. We are solving for Q, so we'll just leave Q there. E is 5, but notice that this is our drawing. So it's telling us that these 4 arrows represent the electric field, and this arrow represents the distance that we've moved, the 0.4 meters up. This is the distance. Okay, so the electric field is down, so we're going to fill that in as negative 5, and the distance that we moved is up, so we're going to plug that in as positive 0.4. Alright, so let's go ahead and solve for Q. We need to take 9 divided by negative, divided by negative 5, divided by 0.4. Actually, this negative and that negative cancel out, so we'll just skip that. So it will be 9 divided by negative 5. Well, we already canceled out the negative, so 9 divided by 5 and divided by 0.4. And I get 4.5. We're still in scientific notation, which puts that over there, so let's just go back to float. So it's just 4.5. So Q equals positive 4.5 coulombs is the unit for charge. Okay, just to be clear, down in this formula, we are plugging in our positive and negative signs, which means if we solve and get a positive Q here, it means that the charge is actually positive. Whereas up here, all of these numbers are going to be, we're going to plug them into the formula as positive. So if we solve for something, the answer is not necessarily positive or to the right. It could be to the left, or it could be positive or negative, right? We need to go ahead and check based on the situation. Okay, let's put a box around that one from before, and let's fill in positive 4.5 coulombs over here. Positive 4.5 coulombs. All right, let's keep going. Question 5. Halfway there. There's a potential difference of 6 volts. Potential difference is delta V in moving 12 centimeters to the left. So this is the distance, and it has to do with delta V. So we're down here, so the distance is going to be D. This right here is D. In electric field E, what is the magnitude and direction of this electric field? So we got to solve for electric field. Okay, so the equation that relates it, delta V equals negative E times D. So let's plug in what we've got. We're told that the potential difference is positive 6. The electric field is what we're solving for. And the distance is 12 centimeters to the left. So first off, it's 12 centimeters. In physics, we need to use meters. Like, notice that's in meters. All of our units should be in meters. And the conversion is right here. So in order to go to meters, we've got to divide by 100. So 12 becomes 0.12. Also, it tells us that this distance is to the left. And in this equation, we need to plug in positive and negative signs for each one. So to the left is going to indicate that this distance is negative. So again, we've got a negative and a negative, which will cancel. So we'll just do 6 divided by 0.12. 6 divided by 0.12. And I get 50. So E equals 50 newtons per coulomb. Now, I got a positive number here. So what does that tell me about the direction? Because they want to know the magnitude, the number, which is 50, and the direction of this electric field. Well, we called left negative, which means that positive must mean to the right. This is to the right. Let's go ahead and fill this in on our answer sheet. So it's going to be, direction. To the right, the magnitude is 50. The unit is newtons per coulomb. Okay. Next, number 6. What is the force on this charged particle? Okay. So in order to solve for force, if we're given electric field and charge, which is Q, and we're solving for force, the formula is going to be F equals QE. Okay, and we're just going to plug in all of our numbers as positive over here. So we're solving for force, so it equals Q, which I'm not going to worry about the negative sign, we're just going to do 4E. Now, the charge is 4E. It's not 4 coulombs, which is the unit for charge, it's 4E. So that's telling us that there are 4 either protons or electrons. Since it's negative, I know that it means 4 electrons. So over here, the value of E is this number right here. So we're just going to substitute in 4E, we're going to substitute in 1.6 times 10 to the negative 19th. So this right here is our charge, 4E. Alright, and now we'll plug in E, which is 20. Again, we're not going to worry about left and right, positive or negative for this problem, because in this formula, we're just going to plug in everything as positive. So if we multiply this out, we have 4 times 1.6 E negative 19, and we're going to multiply that by 20. So I get 1.28 times 10 to the negative 17th. And this is force, so it's measured in newtons. Now, on my answer sheet, I have to report the direction as well as the magnitude in the unit. So let's look at our picture to see if we can figure out the direction. So the electric field is pointed to the left, which means that if this were a positive particle, it would move to the left. But it's a negative particle, so it's going to move in the opposite direction of the electric field. So instead of with the electric field, like a positive particle would go, it's going to go opposite the field since it's a negative charge. So the force is going to be to the right. So our direction is to the right, 1.28 times 10 to the negative 17th. And this is force, so the unit is newtons. Alright, number 7. In the hydrogen atom, there's a single proton. What do we know about protons? We know their charge. Orbited by a single electron. What do we know about electrons? Their charge. So, in fact, this is going to be Q and Q. Both of our Q's are both this same number. They are separated by a distance of approximately that distance. Okay, so that's one of our distances. What force does the proton exert on the electron? So we're solving for force. So what equation relates force to Q, Q, and distance? So R, well, it's going to be this one right here. It's called Coulomb's law. So force equals K QQ over R squared. So we're solving for force. So F equals K Q1 Q2 over R squared. So we'll plug in the value of K from our formula sheet, 9 times 10 to the 9th. We'll plug in the value of Q1 and Q2, which is just a proton and an electron. So 1.6 times 10 to the negative 19th, 1.6 times 10 to the negative 19th. Now notice we're plugging in all of this as just all positive numbers. So we're not going to worry about the fact that a proton is positive and an electron is negative. We're not going to worry about that. We're just going to plug in positive and positive. All right, and we need to divide that by this distance squared. 5.3 times 10 to the negative 11th squared. All right, let's do this in our calculator. 9e9 times 1.6 e negative 19 times 1.6 e negative 19 divided by, let's go ahead and put this in parentheses since we're going to square it, 5.3 e negative 11 squared. Enter. Again, let's put this in scientific notation. So I'm going to hit second scientific. So it's 8.2 times 10 to the negative 8th. This is a force, so it's measured in newtons. And recall, on our formula sheet, on our answer sheet, we're going to have to plug in the direction of the force. So we're looking for the force on the electron. Well, keep in mind that these have opposite charges, so they attract each other, which means that the electron's getting pulled in and the proton is being pulled toward the electron. So these attract each other. So the question is, what force does the proton exert on the electron? So what's the direction of the force on the electron? So the force is going to be to the right because it's a force on the electron, which is being pulled to the right toward the proton. So let's plug in this force with this unit in this direction. So to the right, 8.2 times 10 to the negative 8th. And the unit is newtons for force. All right, we'll have one question left. Find the net electric force on Q2. All right, whenever we're told that we're supposed to be finding the net force or the net field or the net anything, it means that we need to add up all of the individual forces or all the individual fields or all the individual whatever they are. So how many forces are exerted on Q2? Well, Q1 is going to be pushing or pulling on Q2, and Q3 is going to be pushing or pulling on Q2. So we're actually going to solve for force between these two, and we're going to solve for the force between these two, and then we're going to either add or subtract them. So let's solve for each of those forces. So how do we solve for force between two different Q's? It is this formula right here. Do we have everything we need to solve for force? We have K, which is this number. We know Q1 and Q2. Q1 and Q2 are 1 and negative 2. And do we know the distance between them? Yes, it's 6. So let's go ahead and do that. So F equals K Q1 Q2 over R squared. So let's plug in. 9 times 10 to the 9th is K. Q1 is just 1. Q2 is 2. Again, we're just going to plug in all these numbers as positive and not worry about our positive negative signs right now. We need to divide it by the distance squared, which is 6 squared. So let's do that. 9 times 10 to the 9th times 1 times 2 divided by 6 squared. It's 5 times 10 to the 8th. All right. Let's do this again, but instead of Q1 and Q2, we'll do Q2 and Q3. So K is 9 times 10 to the 9th. Q2 is 2. Again, we're not going to worry about positive or negative signs. Q3 is 3. We'll divide that by the distance squared, which is 3 squared. So we'll do the same thing. 9 times 10 to the 9th times 2 times 3 divided by 3 squared is 6 times 10 to the 9th. Newtons, because it's force. So the question is, I've got these two different forces, so what am I going to do with them? Should I add them or should I subtract them? Well, let's look back at our picture. So Q1 is positive, Q2 is negative, Q3 is positive. So when we look at the force just between Q1 and Q2, they're going to be attracting each other. So Q1 is being pulled this way, and Q2 is being pulled that way. So that's this force on Q2 is this way, to the left. So this one is to the left. Okay. This force of Q3 pulling on Q2, well, it's also being attracted. So it looks like this force is pulling to the left, but this force is pulling to the right. Okay, so with these two forces, since they're in opposite directions, I should subtract them. So we'll do 6 times 10 to the 9th minus 5 times 10 to the 8th. We get 5.5 times 10 to the 9th. So our final answer is 5.5 times 10 to the 9th. Now, newtons. Now, which direction should I keep? We're going to keep the direction of the bigger number. So which force was bigger? What's bigger, 5 times 10 to the 8th or 6 times 10 to the 9th? 6 times 10 to the 9th is much bigger. So we're going to keep this direction. It would have been the same thing if we had subtracted them in the opposite order. 5 times 10 to the 8th minus 6 times 10 to the 9th. We still get 5.5 times 10 to the 9th, but we're not going to look at this negative sign. We're just going to keep the direction of the bigger one. So we're going to keep the direction of this to the right. Okay. Let's fill this into our formula sheet. So it's to the right, and it is 5.5 times 10 to the 9th newtons. Okay, that is it for all of the regular problems. If you want any help with the extra credit problems, feel free to come see me.